use that data from the video, in incorporating that into our representation. And so what we have here is a predictive digital twin of this human organ. Now again, this is very much early days. This is not something that developed to building information management. And in many ways, just having those geometric representations is a huge amount of information. You saw Theo's representation of Monument in London, where you had a mesh that represented the actual buildings. This is like a development area for rail travel. And you can see the interaction, so actually selecting whole components and then selecting individual components from the whole assembly, querying where they are, querying what are their characteristics. And this is incredibly powerful. Laying out something as complex as a multi-story building without even without doing it in reality, and doing it in this virtual reality within the digital twin. Hugely powerful. And yet all we're doing is taking geometry, taking constraints as to what can go where, what can be joined with what, and representing it. And that's fairly powerful. But we can go further. We can now think about how do rational, or in some cases irrational, humans actually operate and interact in an environment. Could we, for example, have a digital twin of an underground station and ask questions such as, what is the peak flow of people that are going to be moving in and out of this? What happens if, for some reason, a small number of people get startled because of some incident? How is that going to ripple through? And what are the potential consequences? Well, digital twin technology allows us to do exactly that. So what you're seeing here is a representation of the geometry and of the constraints in this spatial location. And in addition to that, we have these twins. Now these are definitely not identical twins. These are definitely lots of little Danny DeVitos. But they're twins in terms of the rules that would govern rational actors walking about and interacting in this particular setting here. And so this agent-based representation interacting with the BIM-type representation gives us something incredibly powerful. We can now study the socio-technical interaction and influence the actual design and look at potential scenarios. So, extremely exciting. Let's move on to something different. We have colleagues at the University of Southampton who are partners of the Alan Turing Institute, and they have established a marine and maritime engineering programme. And what you're seeing here is a digital twin of a new propulsion mechanism for ships. Now you can see it's clearly biologically inspired, but the twin, in this case a physics-based representation along with the geometrical representation, shows how it interacts with, in this case, the fluid that is propelling itself through. And unfortunately, what I wanted to have was the video showing the actual physical representation of this ship but unfortunately it was too late. They just got it working by the time I had to send in these slides. A very exciting work. Again, a digital twin representing and allowing designers to look at different types of design, and in this case here for propulsion. This project here is really cool because what this has done is developed 3D printing technology to such an extent that a pedestrian bridge has been 3D printed in stainless steel. It's the world's first. And our team at Turing were called in because the company that developed the robotic technology to print a structure of this size, they came to us and said, we've convinced the city of Amsterdam to put this pedestrian bridge in an area of Amsterdam that needs rejuvenation. So it's going to be a big thing. It's going to be, it's going to attract a lot of visitors, a lot of tourists, and it's going to be used for various civic events. And they came to us and said, we've designed this, we're building it, but we don't know what the material properties of 3D printed stainless steel are. And we don't know what the structural properties are of a structure that's constructed in this, or printed in this way. Can you help us? And so I gathered a team of structural engineers from world leading from Imperial College, gathered a team of Internet of Things sensors people from Cambridge University, pulled a team together from Exeter who had been studying composite materials, and even mathematicians who had been looking at stochastic geometry and so on. And we built a digital twin, which you'll see shortly, of the actual structure. We used data from the structure to characterize it and to help us understand what exactly the structural properties were and whether we should be really flying over to Amsterdam and taking a walk over it at some point. And the key is that yes, it is safe. It does deform plastically at some loading, and we were able to use advanced modelling methods, in this case finite element methods, which have been developed to not just solve the mathematical equations that govern the deformation of a bridge like this, or a structure like this, but also to assimilate data from the actual physical, its other twin, if you will. So this is really exciting work. Let me just change tack and move away from structural engineering to a team that we've got at Turing of aerospace engineers that are working directly with Rolls-Royce, and they're seconded from the Whittle laboratory. And what you can see here is, so there were 3 particular engines, and what we were able to do, again using virtual reality technology, is take the actual digital twin of the gas turbine to pieces and actually look and see how do the various components of the engine affect its performance. And it can do this by, again, taking data from the actual physical gas turbine and querying that along with the actual digital representation. So we have this twin that allows us to gain insight and to study the performance of the actual engine. But we can also have a digital twin of a complex thing like a gas turbine to not only study its performance, but to look at implications that a change of design would have. And what you're going to see here is a study in which we can look at multiple designs of the big fan blades at the front and look at what the implications would be for the overall characterization of the gas turbine. So if you remember our little physical twins that we started off looking at, they were very much bespoke one-offs. If we wanted to look at a different wing configuration, we'd have to build another model. Here, what we're able to do is actually select multiple types of design, here we go, and compare them, and do that almost ad infinitum. So this is a huge step forward as far as the design of complex systems such as a gas turbine. Let's stick with aerospace, but rather than just looking at the propulsion systems, let's actually look at the control of the whole environment, right? The whole airspace, making sure that it's safe, making sure that we can pack in as many aircraft as possible, get them in and out of the UK without any incident at all, and with the least delay possible, of course. Right? So we have safety, we have economy, in many ways two competing criteria. And we have our partnership, so our data-centric engineering program at the Turing has a partnership with the National Air Traffic Service, where we're developing new AI technologies to improve the quality of air traffic control. And quality of air traffic control is measured based on safety, measured based on throughput, and therefore economic performance. Again, one of the key things here is developing a digital twin of the overall airspace, and using that in terms of what-if analysis. What if we allow smaller distances between aircraft on takeoff and landing, and so on? Again, these are the sorts of questions that we couldn't really ask without digital twin technology. Okay, let's really go crazy. We've seen digital twins of buildings, digital twins of assets like gas turbines. We've been talking about digital twins of the weather system, digital twins of UK airspace. And I said that the UK government issued a challenge to develop a national digital twin. And there are some colleagues here from Manchester who are leading in the development of this national digital twin. And in many ways, this is exactly the vision that we have. That we have a built asset, whether it's a 3D printed pedestrian bridge or a building. We have a whole system of assets, an urban environment. We have a whole borough, a whole community where people interact and worry about things like localized air quality and how retail, right? How social and economic interaction actually happens. And of course we can scale that up into regions and cities, which is exactly the sorts of things that companies like Amazon are interested in. How do I get this product from A to B in the shortest possible time? And then, of course, moving up to a whole nation. And we're on the cusp of seeing the development of technology that would provide the UK with what we call a national digital twin. And here's something here where, again, we have this twin now at a regional level, and the amount of data, so here is data, environmental data, and highlighting where every tree is, where every piece of green space is, and overlaying that on, again, multiple different types of information. There's an asset, and within the asset, of course, we have all of the information about, measurements of in this case here, this happens to be, if I remember, air quality, or air temperature, sorry. And you can see how we build everything up into what is a twin of this particular region. And on it goes. So hugely exciting. But what we require is a synthesis within digital twin technology of both artificial intelligence, computing, mathematics, statistics. Of course, you'd expect a statistician to say that. And all working together to provide us with this great new dawn, I would say, that we're on the cusp of actually seeing. And this is just an artistic representation of exactly the sort of thing that Theo has been describing. You can now start to think about cities. The benefits we spoke about are economic, interconnectedness, better decisions, safer decisions, securer decisions, greener, healthier. There are lots of challenges, technical challenges. The future of medicine, the future of engineering and manufacturing. So digital twins, I would say, really are the next phase of the AI revolution, and it's a very exciting time to be playing a part of that. So thanks very much for listening. I'll hand you over.